And good evening, Year 13. Okay, here's a question that I made earlier, or that I answered earlier. So I'll go through the workings now. You can read the question over here. Okay, and so, here's what happened. So, the question is, what is the speed of car A, the first part of the question, at the start of sliding just after collision. So, firstly, we've got ourselves a Suvat equation. We've got ourselves a Suvat question. Okay? Now, although this isn't a Year 13 topic, Suvat equations obviously came up in Year 12, you need to remember them. It's not a skill that suddenly disappears. So what you've got is you've got the distance as being 8.2, and when it comes to a halt, it will be 0, speed will be 0. And then you can take the coefficient of friction. Now the coefficient of friction is what defines the frictional force, and it's equal to mu r, where r is the resistance caused by the contact between the car and the ground. So the contact resistance is equal to the weight in this case. So the force is equal to 0.13 times by the weight, so that gives us this value, and then if we divide by the mass, we get the acceleration. So obviously a lot will cancel here, so we've got an acceleration of 1.3 meters per second, although obviously in this case it's a deceleration because it's the resistive force. So we can use this deceleration, this minus 1.3, in our Suvat equation. So we take our 8.2 meters per second as our distance, and v being our final speed, and we can substitute the values in here. And we can do that to find the initial speed, u. So by substituting, we can rearrange, and then we find, I've just done some simplification here. Okay, so this comes to the other side, it's simplified and then square rooted, and that allows us to make this here. So we get a final value for u as 4.62 meters per second. Now you then need to repeat the same process again for part B. So the car B at the start of sliding, just after the collision, is a Suvat equation. So we've got final distance travelled as 6.1 meters. We get the same acceleration. I'm not going to repeat the process, but it's exactly the same process to find the deceleration. And so I've skipped a few steps because the steps are exactly the same. And I just jumped straight into working out the answer. So we've got u being 3.98 meters per second. So now we've got the two speeds of the two cars, or the two velocities of the two cars immediately after the collision. We can work out the momentum immediately after the collision. And in this case, the total momentum is the mass of car A times by the velocity of car A plus the mass of car B multiplied by the velocity of car B. So we get these two numbers, giving us a total momentum of 10,654 kilogram meters per second, and then we can use that to find the speed of car B. Okay, the question is a little bit incomplete here, but I'm just going to put a full stop in there. The question continues to find the speed of car B. Blah blah blah. So the speed of car B before the collision is all of the momentum, the total momentum within the system, divided by the mass of car B. Now, what assumption have we made here? The question goes on to ask about assumptions being made. So we've assumed that all of the momentum has been conserved, and all of the momentum would be conserved because it's the principle of the conservation of momentum. The condition that you have there is that it's a closed system. So we're neglecting any forces in the collision. Now that might not be valid, okay, because crumple zones are designed to absorb energy and momentum in the collision. You have resistive forces from the crumpling of a crumple zone that are intended to make sure that collisions don't have a conservation of the momentum. Okay, so I hope you've understood that. I hope it's been relatively easy. Look over it again, but it's just a little bit of an extra problem, giving you an extra example